Welcome to the video on Graphical Behavior II, Day 3. In this video we are going to focus on discussing the relationships between f, f prime, and f double prime. And as we know, f prime we use to determine where the slope is positive or negative, and thus the function is increasing or decreasing. And we use f double prime to determine where the second derivative is positive or negative, and thus the function is concave up or concave down. So we're going to kind of combine the last 2 days, last 4 days actually, into one kind of summation lesson. All right, so let's get to it. What we have here in example 7 is the graph of the derivative. So this is not the function, but this is the derivative of a continuous function. And it tells us that it goes from 0 to 9. We don't really have 9 plotted here, but I'll drop it on there. And they want us to answer the following questions in complete sentences. And this is a common free response type question on the AP test, so being able to draw these connections is going to be really useful to you if you're trying to score well on the test. So I'm going to zoom in here to give myself a little bit more room. On what open intervals is f decreasing? And remember, f decreasing means that f prime is negative or less than 0. So we want to look at the function and see where the derivative is less than 0. And we see that the derivative is less than 0 from 0 to 1 and 6 to 8. So we state what we know. F is decreasing on 0 to 1 and in union with 6 to 8. And then we need our justification. And we always base our justification off of what we're given. And we're given the graph of f of x. So we write because the graph of f prime of x, I think I said f of x, we're given the graph of f prime of x is negative on these intervals. So alternatively, we can very shorthand write that because f prime of x is less than 0. So the blue text here is kind of a more complete presentation, whereas the black text is just getting it put on paper as quickly and concisely as possible. Okay, at what values of x does f have a local maximum or a minimum? And we can use f prime, the first derivative, to find the local max and min by using the first derivative test. And remember, the first derivative test says that if a function changes from negative to positive, then we are going to have a local minimum. Or if a function changes, the derivative changes from positive to negative, we will have a local max. So right here we get our local min. We also have a local min at 8. And then at 6 we have a local max. So here we go. Let's write that out. F of x has a local min at x equals 1 and 8. And f of x has a local max at x equals 6. And the reason for that, we always have to include a justification, is based off of the derivative, because f prime of x changes, remember minimums go from negative to positive, so it changes from negative to positive. And then the conclusion here is because f prime of x changes from positive to negative. And the order is important. What we're citing here is the first derivative test. And keep in mind we're given the derivative, so our justification needs to be based off of what we are given. Okay, part C asks us to determine where the function is concave up and where it is concave down. And remember, concave up means that the second derivative is positive, or you could say that the first derivative is increasing. So since the first derivative is increasing here, the derivative from 0 to 2 would be positive. Thus, the second derivative of the function is positive from 0 to 2. So all locations where the first derivative are increasing would be locations where the function is concave up. And where the function is decreasing, where the derivative is decreasing, the function is concave down. So we can write this out that f is concave up on 0 to 2, 3 to 5, and 7 to 8. And then f is concave down on 2 to 3 and 5 to 7. And then we need to write the justification. The justification is based off of what we have, and we can say because f prime of x is increasing, or concave down because f prime of x is decreasing. So that's the justification based off of what we are given. And I'm going to add in here, if f prime of x is decreasing, you could say f double prime of x is less than 0. All right, part D asks us to find the points of inflection, or the inflection values, and those occur where we switch from concave up to concave down. So since our function is concave up here and then concave down, i.e. the derivative is increasing to decreasing, points of inflection are going to occur anytime the derivative changes from increasing to decreasing. So we have, it looks like 4 points of inflection, so, or values of inflection. So the value is x equals 2, 3, 5, and 7. So let's write this down here. There are inflection values at x equals 2, 3, 5, and 7. We can't label them as points because we don't know the original function, and thus we don't know what the y coordinates are for these particular x coordinates. Anyways, the justification, again, base it off of what we are given. Because f prime of x changes from increasing to decreasing, or vice versa, or decreasing to increasing. Okay, finally part E is what we're going to do is we're going to try to sketch a graph of what f may look like based off of the graph of our derivative. And I'm going to go ahead and do that on the graph here. And we've found all the information that we need. We know that our function is going to be concave up from 0 to 2, and it has a minimum at 1. So what we can do is we'll draw, I don't know where the minimum occurs, we'll just say it occurs there. The function they told us starts at 0, 0, and we want something that's concave up but has a minimum at 1. So there we go. And then from 2 to 3, we want the function to be concave down. So from 2 to 3, we're going to draw something that's concave down. from 3 to 5, we want concave up. So we'll go 3 to 5. We'll draw something that's concave up, and that's because the derivative is increasing. And then from 5 to 7, we're concave down. This is concave down with a maximum at 6. So somewhere up here, we'll hit our maximum, and we're going to be concave down all the way to 7. So maybe something like that. And then finally from 7 to 8, looks like we are concave up, and that we hit a minimum at 8. So somewhere around 8 we'll hit our minimum, and we're concave up. There we have it. That's what the graph could look like. Now keep in mind this could be stretched vertically. It could be shifted up or down, except we're told where it starts. So this is just a very loose approximation of what one possible function may look like.
Visions of our love pass right by me. Your eyes are enough to remind me. Visions of our love pass right by me. Your eyes are enough to remind me.
Okay, in example 8 we're doing the exact same thing where we're given the graph of a derivative, and we're going to ask some of the same questions and then sketch what the function looks like. So what I'm going to do is I'm going to let you take a shot at doing each one of these, and then we'll discuss it. I'll write out the answer and we'll discuss it. So for part A, go ahead and pause the video and see if you can come up with the right answers, and then check against the video. Go ahead and pause now. Alright, so the function is increasing from 0 to 2 because the derivative is positive, 4 to 6 because the derivative is positive, and 8 to 9 because the derivative is positive. Go ahead and take a shot at part B, and I'll pause the video here and put in the answers. Go ahead and pause. Alright, we have two local maximums. The first occurs at 2 because the first derivative changes from positive to negative, and the second one occurs at 6 because the first derivative changes from positive to negative. Now this jump here does indicate something kind of interesting. The derivative doesn't exist there, so what we probably have going on in the function is our increasing slope to a maximum, and then it decreases. So what we have is a cusp located at x equals 6. Now the local minimum. For the local minimum, we have a local min at 4, because the first derivative changes from negative to positive, as well as one at 8, because we have another change of the derivative from negative to positive. Part C wants us to find where the function is concave down, so go ahead and do that. Pause the video and I'll write in the answer. Alright, we only have one area where the function is concave down. It's from 0 to 3, and that's because the function is decreasing there. They want us to find the points of inflection, and we know that points of inflections occur where the function changes from concave down to concave up. So in part D, we have inflection values at, F has inflection values at x equals 3, and only 3, because that's the only spot where f prime changes from decreasing to increasing, so, or vice versa. There's our reason f prime changes from decreasing to increasing, or vice versa, at these locations. Okay, and finally in part E, they're asking us to sketch a curve again, assuming that the function starts at 0. So going up here, our function starts at f of 0 equals 0. We attain a maximum at x equals 2, and looks like we're going to be concave down from 0 to 2. And we continue to be concave down until 3. So somewhere over here we're going to continue our concave down part of the curve. From 3 to 4, we are concave up with a minimum occurring at 4. So we got something like that going on. From 4 to 6, we are concave up. So comes into that cusp that I've drawn there. And then finally, we have a minimum at 8, but we're concave up all the way from 6 to 9. So we get something kind of like that going on. So there's a possible graph. Okay, finally I want to draw your attention to this fun chart that's been popping up on pages down at the throughout pages. It's a useful tool to help us memorize the relationship between all of these things. If we want to know where a function is increasing, what we're going to do is we're looking for where the function is increasing. We'll see it where the first derivative is positive. So if I want to know where a function is increasing and concave down, we're going to look for spots where the first derivative is positive and decreasing. So we can use this fun chart to help organize our thoughts. It'll pop up randomly through the pages, and we'll get some more practice on it as we progress through the rest of graphical behavior. Okay, thanks for watching Graphical Behavior Day 3. Hopefully here you've started to solidify some of your relationships between the function and the derivative, telling us where a function's increasing and decreasing. And hopefully you can work backwards, where if you have the derivative, you can tell me about the function. Or even better, if you have the second derivative, you can tell me about either the derivative or the function. So we'll give this this type of work a few days of practice before we move on. So let's work at solidifying this, and thanks for watching. Have a good evening.